Back. Um, Today's topic is tornadoes as we continue our campaign. I think we all have a pretty good definition of what a tornado is. A violently rotating column of air, and obviously one of the most destructive forces of Mother Nature. So what we're going to cover in this video is real briefly going to touch on tornado climatology, some science that goes into developing tornadoes. We can take a look at some radar images, and also, last but certainly not least, touch on tornado preparedness. So spring is the main peak time for tornadoes in Indiana. March, April, May, and June. June and May tend to be the biggest months, but we can, and certainly do, see tornadoes and tornado outbreaks during April and March as well. We have a secondary peak that comes during the latter half of the fall season, particularly late October into November. And then the most important thing to remember is that tornadoes can happen any time of the year, especially in this state. Not so much in other places in the world, like for example, in the South, they get hammered pretty hard with tornadoes earlier on in the spring and during the winter time. But eventually the jet stream, which is a driver for a lot of the wind shear and dynamics, begins to pull further to the north and eventually just gets so out of range from the southern states that they begin to lose the capability of tapping into those finer dynamics. And then the same happens for the northern states. During the summertime, the jet stream sets up there closer to the Canadian border, but eventually it retreats to the south, and before you know it, they're getting blasted with colder temps and snow and blizzard conditions. But Indiana just happens to be in that perfect location where we are close enough almost any time of the year where we can tap in to those finer dynamics and see tornadoes across the area. Tornadoes do occasionally happen during the summertime, and they're not unheard of during the winter as well. So it's always something to keep in mind. Okay, quick look at some of the parameters that we look for when we're forecasting tornadoes. One is instability, which is basically the fuel for thunderstorm development. That often comes from the sunlight. Basically, uh, in order to get thunderstorms, you really need something to grow an updraft. Instability is basically the fuel that mixes with the moisture, allows for the clouds to condense and build into an updraft for the thunderstorm. Updraft is basically the center part of the thunderstorm, kind of like the brains of the thunderstorm. We'll talk a little more about that tomorrow when we get into supercells for the topic. So, but basically, if all you have is dynamics, but you have no instability, you're going to have nothing but a rainy day. If you do get instability, even if it's marginal, these updrafts will begin to grow, and then you can get thunderstorms out of them. Now during the wintertime, you don't need a ton of instability if the dynamics are off the charts, especially. But you do need something to allow that updraft to grow. You need something to condense and allow the clouds to tower and allow the development of an updraft. Again, we'll talk a little more about the structure of a thunderstorm here tomorrow. Obviously, you also need moisture. This is a little more self-explanatory. Although moisture is not solid, it's basically, food for the storms. If the storms do not have moisture, they will struggle to maintain themselves. And then one other thing, and this is particularly important when it comes to tornadoes, that is shear, the changing of wind direction within the atmosphere. This is basically rotation of the winds that's occurring higher up there in the atmosphere. If you have instability and moisture, you're going to get a thunderstorm. If you have a cold front or a boundary or whatever to trigger, to basically pull the trigger and allow storms to develop, then you're going to have a thunderstorm. But if basically the instability and the moisture is all you have, the thunderstorm's just going to rain itself out. The rotation, the low-level shear, is rotation that up there within the atmosphere It basically maintains the thunderstorm and keeps it going for a longer period of time. The rotation sustains the updraft. The rotation keeps the updraft going, basically. And when this happens over a longer period of time, the thunderstorm then becomes a supercell. And again, we'll talk a little more on supercells tomorrow. But the wind shear is important because the rotation is what sustains the updraft. And eventually, when that rotation within the updraft, which is called a mesocyclone at that point, begins to get strong enough, it will lead to the development of a tornado. Something else that we look at is storm relative helicity. This is basically the measure of low-level shear from the surface to about 1 to 3 kilometers above the ground. This just kind of gives us a better idea, basically, as to how intense the turning of those winds, that rotation really is. It's kind of hard to explain it, but that's just kind of the best way to explain it to amateurs like a lot of you who will be watching this video, or rookies. If you want to know more, I'm thinking about maybe even doing more videos after this week is over to kind of explain some of the stuff a little more in-depthly. But the bottom line is these are four of the most important things to consider and look at when it comes to forecasting severe weather, and particularly tornadoes. There's a whole book basically that you could write on, full of different parameters and different things to look at when it comes to tornadoes, like heights and capping inversion and all that kind of stuff. There's just so many out there, but these are generally considered to be the four most important things when you're looking for an organized severe weather threat. Okay, so now we're going to switch gears a little bit, and we're going to take a look at radar, and we're going to take a look at trying to detecting tornado signatures on radar. Now, this first picture here on the left, you can see we have a thunderstorm. This is the thunderstorm that produced the Moore, Oklahoma tornado, not the recent one, but the one back on May 3rd, 1999. You can see we have a thunderstorm, heavy rain, probably some hail within here, and it looks just like any other picture that you're using to look like, that you're used to look at. I can't talk today. That you're used to looking at on TV. But I want you to notice this feature right here, this little appendage like feature. Now I want you to we're going to switch gears. We're going to go over here to this picture. This is what we call storm relative velocity. This is a product that comes with Doppler radar that allows us to look at the winds within a thunderstorm, and this allows us to detect rotation. Red means the wind speeds are going away from the radar. Green means they are going towards the radar site, wherever the radar site is located. Look at all this red here, but then look at this little area of green right here, wrapped in nicely within the red. Obviously, that means that we have a change in the wind direction right here in this area. That means that we have rotation. So, assuming the tornado was down at this point, which judging by that look, it probably was, this would have been right where the tornado is, right here. We call this a couplet when we see the red and the green touching each other like this. And then if we go back to the reflectivity data, this is what we call the data that you're used to looking at on radar. We kind of, again, I want to note this feature right here. See how it kind of lines up. Here's more on that picture. You can see where the green and red are touching each other. Here's more again. And you can kind of see right here how this thing is looking. This is a debris ball, basically. This is where the rotation the tornado has gotten strong enough to the point where it's actually lifting and tossing debris up into the air. And technically, you cannot really know that there is a tornado for sure on the ground until you actually visually spot it. But this is basically, when you see something like this, it's basically an indication that something is definitely on the ground, most likely a strong tornado. You can see that white pixel. I'm going to point that out in particular. You can see the heavier shaded colors, the pixels, are the darker reds, are all up here until you get to this little appendage right here, and then all of a sudden you got a white pixel. Again, this is the radar detecting debris and damage being aloft by the tornado. And so, in this case, you really don't even have to look at the velocity product to see the tornado. Again, here's another look. I'm sorry it's blurry, but here's another look at the velocity product with a different thunderstorm. And here again, you can see green, but wrapped in within that green, we have a nice red area. Winds moving away from the radar site as opposed to moving towards the radar site like the green. Here's the radar right back here, I believe. And you can actually see this is getting to the point where the colors are maxing out. You can see dark, it goes from green to dark blue, and you can even see some pinker and white colors showing up within that red. And that means the rotation is basically very strong. That is more than likely a very significant tornado on the ground. So that's just a little more on the velocity product and how you can look at thunderstorms and look at possible tornadoes on radar using the velocity. Again, I know this is I'm kind of squeezing everything in here, but I'm thinking about maybe later on going back after this week is over, going back and doing videos to explain the stuff a little more in-depthly. And if you have questions, you can always ask. Here's another look at the radar, and again, you can see a thunderstorm. This would have been the Joplin tornado. Heavy rain, hail, and then right here we see another little appendage. We call this a hook echo. And we see the purple right here, little white dot showing up in there. This is most likely where that EF5 tornado was throwing up a lot of damage and causing a lot of major problems. Obviously, that was a very significant tornado. So switching topics here real quickly. Let's talk, now that we looked at isolated storms and looking at tornadoes with isolated storms on the radar, talk a little bit more about tornadoes that develop along QCLSs, or those big squall lines. Tornadoes that develop along those big lines of storms, again what we call QCLS or squall line, they tend to spin up very quickly, typically very brief and weak. So there's a plus and there's a negative there. Plus is that they do not last very long, they're usually weak, but the fact that they can spin up quickly means that you still don't want to estimate them just because their strength may be minimal. Doesn't mean that they can't cause a lot of problems, because if a tornado, anytime a tornado sneaks up on you, it's never a good thing. It doesn't matter if it's EF0 or EF1. Any tornado can do damage. Any tornado can kill. So just because it's weak and doesn't last very long doesn't mean that it can't cause problems. And here we are looking at a squall line right here, a big line of storms. I want you to notice something on this picture here in particular. We had this little area, and you can see it is a little appendage right here. Let's take a look at the velocity around that time. And although it's broad, you can kind of see a little bit of rotation here. You can see brighter red, a little bit of brighter green. They're kind of coming together here. If you go back a little bit and you look on this picture here, the velocity, you can see brighter red again, brighter green. They're kind of coming together a little bit. And I want to point out how they kind of get brighter as the colors get closer to touching each other. So that right there could be an indication that we have a little bit of rotation within that storm. And whenever you have rotation along a squall line like this, it can be harder to detect. Harder to find the tornadoes within the squall lines because they can be so small and so quick. So real quickly, tornado preparedness. Basement or storm shelter is the best bet. There are some buildings that have older bomb shelters, older fallout shelters that might work. And I keep finding more typos in here. Depending on their age and location and their structure. Obviously, if you have a bomb shelter at the top of the building, you don't want to be there. Lowest floor, if you do not have a basement or storm shelter or whatever, lowest floor, preferably a small interior room, no windows at all. At the very last resort, at least get into a hallway, an interior hallway, lay down. Wherever you take shelter at, cover yourself with something like a hardback book. Maybe put on a bicycle helmet. I've heard people say that, bicycle helmet. Abandon all mobile homes and vehicles, absolutely. And every place, this is important, every place should have a plan, not just homes. Schools, businesses, every place. Thank you very much.